Devashish Paul. I now have my green jacket on, which is as a co-chair of the High Performance Computing Group. So when I just presented in the telco track, I wore my regular jacket, I guess. And now I got my OCP tracksuit on. I've got my Usain Bolt track spikes on because we're going to go high speed at HPC now. So from the HPC side, there's some genesis here about how we arrived at kind of similar platforms that I'm going to show here for the telco group. So a bit of background. I don't know how many of you guys have met Cole Crawford. Cole was the former COO of Open Compute Project, and I was coming to the OCP networking and server groups and talking about low latency computing. And I kept pounding on low latency computing, and the server guys were like, yeah, but that's not in the Facebook plan of record. And then there were all these like HPC guys from the government and from financial and so on. And they were like, no, hang on. What these guys are talking about makes a lot of sense. So, maybe we need to have a group in the Open Compute Project that's focused on high performance computing. So I'll explain some background on what went on in HPC, and I do want to apologize a bit to the community in terms of the lack of activity on the HPC group. I was injured for a number of months, and I'm just getting better, so I wasn't actually able to. I was just trying to stay on top of my day job and did not progress the HPC activities in the industry or like I would prefer. So when we started off the HPC group, we had a fairly wide charter that was kind of everything outside of standard hyperscale servers that required low latency computing. First, a bit about my company. I'm from Integrated Device Technology. We're based out of San Jose, California. We do a variety of technologies that all of you use daily. And we're essentially doing several technologies that are supporting the processors. So we're not doing any processors, but we're doing the timing, we're doing interface technologies, PCI Express, RapidIO, going back to our old VME days. Chips that we taped out in 1998 still make us millions of dollars, believe it or not. We have wireless charging that's in the iPhone and so on. Just wanted to give you an overview of what our company's about and then dive into the HPC project. So back in 2014, we said, okay, if we form an HPC project, what should its goals be? And I would like to get some of this back off the ground and some of it accelerated, but we wanted an open industry forum where people from the HPC world could collaborate and talk about the needs of HPC and what platforms would be needed, and help define open standards for those, just like we're doing in OCP in server networking. So if you were a medium scale or small scale institution, financial, whatever, wanting to do low latency computing, there weren't a lot of options available to you from the industry. You would just have to buy stuff that was off the shelf and build your HPC. And so what we did was develop a project charter. It was based on heterogeneous computing, being able to connect a variety of processors and accelerators that we often see desired in the HPC world. We wanted to do stuff in an energy efficient way, and you guys can read all of this later, but we wanted to do it in a way where it's not locked into any specific vendor, which of course is one of the goals of the Open Compute project. So that was at a high level, that was our charter. And we wanted to focus on a number of segments. HPC is the name of the group, but it, cover technologies for supercomputing, low latency analytics in the data center. So if you talked with some of the architects of the hyperscale data centers and you asked them, do you care about doing low latency computing? Most of them, actually I talked with one who runs a massive data center, one of the, some of the biggest data centers in China. And he basically said, if you came to me, 3 or 4 years ago, I would have said, I don't care, I just need to slap together a whole bunch of computers and put them in my data center, and then the software guys will take care of everything. And he said, now we are basically looking at optimizing our hardware infrastructure to have low latency computing built in. And so that was kind of like the vision that we would enable that for some of the data center guys. We had, so those of you who were here for my telco presentation, back then we had mobile edge computing in the charter because we felt a lot of the need for mobile edge computing would be HPC-like, but in much smaller appliances. And also for the financial trading guys.
Can I ask a question?
Yes, please
so
go ahead.
What did those x86 core programmers say when you said that we're now going to be championing a heterogeneous software development environment in your standard data center? So what I heard was they were let the software guys take care of it. They're making x86 processors do all sorts of things.
Yeah.
That isn't necessarily what they're best at. So what is the software environment, and how is it changing as a result of your group's initiatives, albeit nascent?
Yeah, so that's a good question. So you're right that most of the applications were running on x86, but I think at the end of the day, the software programmers running the application today don't get to decide what the applications need to do tomorrow, and there's architects for that reason, for the data center, architects for the workloads and all that, who have to dictate how those companies are going to monetize all this free computing. And monetizing the free computing, whether it's Facebook, Google, Baidu, whatever, the computing infrastructure, us users, we get that computing infrastructure for free, right? Like our eyeballs pay for it through advertising, but we get that for free. So realistically, the companies giving us those computing resources for free have an incentive to cost reduce the platform as much as possible and squeeze as much application performance as possible out of it to basically to monetize those eyeballs, right? And so there's architects and there's hardware architects and workload architects working dynamically together to look ahead. An example I was sharing with one of my colleagues this morning, and this really relates to your question, is how well can some of those analytics run? So machines are really good at being able to pull out context from text today, right? But if someone took a picture of me standing here with a green tracksuit on and put it on the internet, there's like analytics engines, like unless you tag the image with some text that says Dev wearing tracksuit, OCP Summit, HPC presentation, if you run analytics on that image, you'd have no clue what this image is about, right? So there is an emerging interest to be able to do like the real-time analytics on the content of the images. That's the first step. But when you get into the video analytics, now you're getting into like a stream of images and being able to pull out context out of that and run analytics on that. And that workload is, it's orders of magnitude more complex than I booked on Expedia in Vancouver, so now let's give Deb a rental car ad for Vancouver. But guess what? I already reserved my rental car, so too late. So the video analytics. So I talked with one of the guys who runs a hyperscale data center workload, and he's like, we're not touching our data center infrastructure now. It's going to be like the typical standard server. But looking ahead 2 years from now, we're going to have to do greenfield deployment to convert our deployments into HPC-like deployments to do video analytics. I covered this slide in the last presentation, but basically what we're saying is to enable those analytics workloads, you need a low latency, energy efficient interconnect that's terminated on die and can do it with a really good cost per performance. So those of you who were here previously, some of this is a repeat, and I apologize for that. These things need to be standalone, but basically the whole idea is the stuff we're doing in the HPC group, we believe there's a big fit for any HPC-like application or workload. When we kicked off the HPC group, we had a board member from Goldman Sachs join the kickoff at UNH in August of 2014. And what he said was, yeah, this makes complete sense. Everything that's kind of in the high-touch computing, it starts in kind of researchy, you know, big government institutions and so on. And then it goes into larger enterprise or hyperscale adoption. And then it just becomes mainstream stuff in due course. So everything that is kind of pointy end at some point becomes mainstream. And that's our vision at OCP HPC. As an open industry group, what we would like to do is basically enable that move from some of this stuff being like niche stuff running in aerospace, avionics, and so on, to being in the mainstream enterprise data center where they're doing HPC. So one interesting thing that we're doing is, coming back to this slide on the RapidIO technology, in IDT's data center, where we have all the software that's running, doing the workload for our engineers who design chips, right? So what we're doing is we're taking a whole bunch of stuff from standard servers and we're putting it on heterogeneous RapidIO servers to actually look at, how much efficiency are we gaining in our own enterprise by converting everything to a low latency computing infrastructure. And on the previous slide, we've shipped 110 million ports of RapidIO, 10 to 20 gigabit per second, largely in the telco and embedded systems. And we see that actually from an HPC perspective, this also adds an interesting volume angle. So on the HPC side, the volumes are typically not as high as hyperscale or handsets and so on. So our volumes are kind of reflective of handset volumes to some degree, because the more handsets you have out there, the more base station technology you need to support all the users. And we're able to leverage those economics to benefit the HPC community. This is kind of the ecosystem around the RapidIO technology. And going back to last year, we've been working with the foundation to enable this to come to market. The technology that I'm talking about, it provides low latency, scalability, integrated on-die termination. And that's something that in the keynote the Intel guys brought up on having 10 gigabit Ethernet on the latest 14 nanometer chip that's 65 watts of the tiny chip, latest Intel chip. So the energy efficiency of the RapidIO protocol is pretty cool, because we have on-die termination already with 20 gig on a bunch of, on a bunch of SOCs in the top group over there. And the latest version with 50 gig, you're going to have 50 gig on-die termination without a NIC or anything like that. So coming to the, yeah, question. Yes. Yes. Okay. I think if I get into a comparison, we'll spend the next half an hour on this slide. So let me just keep it at a really high level and stay back here and we'll talk a bit more about it afterwards. So at a very high level, the only difference between RapidIO and InfiniBand, InfiniBand does scale out, it does low latency. So I would say the biggest difference between the two is in InfiniBand's connectivity to processors is largely not economical to do on die. So there, apologies to my peers from Mellanox, but you have a big honking Connect X3 or 4 NIC chip that's fairly high power, relatively speaking, and you wouldn't be able to suck that into a die easily with the whole processor, with L1, L2, L3 cache and all that. So that, in a subtle way, I think that's the biggest difference between the two. And we're not trying to go head-to-head with InfiniBand or Intel OmniPath. I was on a panel with Barry Davis, the GM of Intel OmniPath, just a month ago. And we're trying to stay at kind of like the analytics appliances. We're not trying to hit the top 500 supercomputers with the RapidIO technology. Ethernet, yes, you have some on-die termination at 10 gig, at 40 and 100 gig. No one's doing it, right? There's a reason.
Cost-effective, integrated into CPU versus a discrete solution.
For Ethernet?
Yeah.
At 10 gig E in 14 nanometer or 28 nanometer, it's very feasible. 10 gig E. My colleagues at Cavium have a built-in 4 ports of 10 gig E switch in their ThunderX ARM CPU. People do 10 gig E on die, okay? Ethernet's, you know, I'm not the chip designer for the 40 gig Ethernet die, right? So I would think that if it was economical, guys would already be doing it today, right? I mean, we're doing it at 20 gig and 50 gig RapidIO. So it's just the protocol termination. Coming back to the comparison really quickly and then we'll move to the next few slides and we'll stay offline here after the presentation and have some Q&A. But the only real difference with Ethernet is being able to do the scale out with low latency. So Ethernet does the scale out at high latency. I kind of joke that RapidIO is Ethernet running on Ethernet rails, but the protocol takes care of the latency. Where Ethernet protocol, I mean, I'm dating myself, but you know, when I used a VAX computer out of college in 1988, and you know, it was connected via, you know, this LAN, and there was this TCP termination and all that cool stuff, right? And it was like, oh wow, look at this, we can connect these computers together. You know, because it wasn't that easy to connect computers together until the guys at DEC and all that came up with some of this stuff. But the whole assumption was there's a processor to terminate the Ethernet protocol. And therefore doing it on die and all that has a processor intervention penalty. So that's the RapidIO, the latest version that we're running. It's running on 10 gig KR and we crank it up to 12.5 gig per SerDes and run it at 50. It's identical, like the SerDes is doing the same thing as you would do in Ethernet. So it's a protocol running on top. That's all it is, right? There's no rock. You know, we've kind of joked around. We should just submit it as a version of Ethernet. It's just a low latency version right now. And in the past, it wasn't on Ethernet, 10 gig KR. but now it is. Okay, really quickly, so this is the converged switch, sorry, server, switch, and storage appliance. So what's cool with this technology is we can actually put all of these things in one 19-inch form factor. So over here you have 4 sockets of whatever heterogeneous computing you want. You got built-in switching that's connecting all of these together with each other, and then you have ports coming out of the back that connect to RapidIO, or you can connect to a 10 gig top of rack switch. There's also built-in storage into this appliance. We have it, a static demo running in the open power booth upstairs with our colleagues at IBM. And the block diagram I have in the top right of this is basically, it's just kind of logically showing that you can plug and play the type of heterogeneous computing you want. We also are launching this x86 HPC appliance with 4 sockets of Intel Broadwell, also into the same platform. And that's basically our partner company, ProDrive Technologies, is taking orders now for that, and it's going to be available for prime time next month. We also have a version with GPU acceleration, and what we did was we took NVIDIA's Tegra mobile GPU, and we actually put 4 of them inside each one of those nodes. So we basically get 1.5 teraflops per node, or 6 teraflops per 1U, which aggregates up to 200 or 0.25 petaflops per rack. We were having an interesting discussion here in between sessions about the power budget per rack, right, for hyperscale. And it can be anywhere from 7,500 kilowatts to 13K to, you know, at the very high end, there's some guys doing 30K, right? So it's a wide range. If you could pack a lot of this GPU technology into a rack, you would just be limited by cooling resource. And we got this RapidIO top of rack switching on demonstration also in the open power booth. We have the 0.75 terabit per second switch, and we launched the 4.8 terabit per second switch just yesterday.
So one is a switch. The Broadwell is a Hadoop cluster, and the other one is a.
You can you're not so on the Broadwell-based appliance. You can run whatever you want on it. So you could run a Hadoop cluster on it.
But it's a batch processing system.
At the end of the day, it's a low latency computing platform. It's optimized for multiprocessor, where you need to shuffle data in between the nodes.
The GPU is a video recognition or a neuro network for neuro analytics.
There could be a lot of applications from the deep learning to the pattern recognition, to the neural networks type of thing. You know, coming back to the telco example, like some of the cloud-based gaming and all that could be run on this, and the vehicle offload and all of that.
So the IDT value add is the RapidIO.
Our value add is the low latency silicon underneath it. So all kinds of guys on top of us will make way more money. We're probably the stupidest smart guys on the planet to get the tiniest piece of the bomb. But anyway, that's how the way the industry works. Just want to give you an example. We're running the RapidIO servers and top of rack switching in CERN's data center, running several of their use cases. So they have a data analytics use case, a data acquisition use case, and an event building trigger use case, all of which would require the low latency computing. So we have that running in our collaboration with CERN Openlab, and that is a 3-year project that we started with CERN last year. Finally, just to enable the HPC industry, what we're doing also, and we're looking at submitting this into the OCP, is creating an accelerator card that's optimized around low latency. So take your standard single socket server and then plug in this NIC card that goes beside it. So it's an FPGA-based NIC card that can connect to our 50 gig RapidIO switch silicon that can connect through a 3D torus to create a 3D torus of high and low latency computing. Or you can connect to a top of rack switch using this. And this is something that is not yet available today. I'm just tabling it as a concept that we're discussing with a number of partners, but we would intend to make it available through the foundation channels. And you could scale it out through RapidIO top of rack switching. So just wrapping up, and those of you who want can stay back here for a few Q&A. We started off this HPC group in 2014, really around doing things that the server and networking group were not doing. Some of these platforms that I'm showing is really genesis out of the work that we've done. We haven't got to the point of going through the submission chain process in OCP. The intent was to do it end of last year, early this year. For a number of reasons, I haven't been able to drive that through. Look forward to your participation. There is an email list reflector for the HPC group. If you have any questions, please post on there, and we'll pick it up from there. Okay? So I can hang around here and take any questions. Otherwise, I'm in between you guys and lunch, and maybe the lineup's already too long to get lunch right now, so you might want to hang out and have some questions anyway. That's all I have. Thanks for those of you online.